Well, I want to welcome everyone to the, what is this? Is April 2022 edition of IndiePie. We are very excited. We got a big update here. As you can see on the screen, we are going to be celebrating our 15-year anniversary. We even designed a fancy logo over there that you can see for our 15-year anniversary. So obviously there will be stickers made for the 15-year anniversary. So you will not want to miss out on that. If you're not going to join us in person, send us a Slack message. Look at that. That's the 15-year already. Man, you're ahead of the game. Justin, you're on it. Love that. So yeah, we'll have 15-year stickers for all of you who come and join us in person May 10th. So next month's meeting will be in person at the district tap. Join us there. We got the back room reserved. There will be cake and lots of fun. Should be a really good time. So we're going to host it in person from 7 to 9 on Tuesday, May 10th. Laura will be sending out some more details in the coming weeks, so look for that in your inbox. Make sure you're registered for the event on meetingplace.io to receive event reminders and updates. That's our official place for getting updates and reminders. So I'm super excited about that. We also want to make sure you're following us on Twitter. So we will be live tweeting tonight. Like Laura and crew will be live tweeting tonight's session using that hashtag and on the IndiePie Twitter account. So if you also want to join in the conversation, that's the way to do it, is right over there. Join and follow us on Twitter. I want to thank our sponsors. First, we'll kick it off with thanking 6 Feet Up. So my name is Calvin Hendryx-Parker. I am co-founder of 6 Feet Up. So IndiePie is brought to you by 6 Feet Up. 6 Feet Up is a Python and cloud expert consulting company that helps innovative tech companies, oh, probably strong music, innovative tech leaders build apps faster, innovate with AI and ML, simplify big data, and leverage cloud technology. Using modern technologies and processes, we make anything possible for our clients. I co-founded 6 Feet Up in 1999, and I've been the CTO ever since. So I want to thank 6 Feet Up for backing IndiePie for the last 15 years. We were here from the beginning, one of the old school Python meetups. Super excited about that. I want to thank JetBrains. So if you hang around right after the talk, I will do a quick door prize drawing. And we've got 2 one-year subscriptions to PyCharm Professional. So do not miss that. We'll be giving away a PyCharm Professional license, or 2 of them. And then the other, well, I'll get to the next one after that, but thanks again to JetBrains. And then our bronze sponsors, Reify Health. So if you've been here previous months, you've heard Jeff give a little spiel. They're certainly looking for lots of Pythonistas to join their team. So check them out. And then JFrog is also an awesome sponsor. They also just renewed, I think, too, to be a sponsor for next year. I think both of them just renewed to be sponsors. So look for more from Reify and JFrog. The other door prize nights, there's 3 door prizes, will be a Adafruit clue from JFrog. So stick around and we'll do the live code drawing like we normally do to pick our winners. You can watch me fumble through some Python code in real time to do the drawing. Oh, and make sure if you want to be in the drawing that you're RSVP'd on meetingplace.io, because otherwise you will not get picked. If you thought those sponsors were awesome and you want to join that rank of those awesome folks, you can by emailing Laura at 6 Feet Up or going to indiepie.org/become a sponsor. And we would love to have you join our crew, our merry band of IndiePie sponsors. We will love to have you on board. It helps us do awesome things and bring great programming. You know, if we need to give grants to people to come to conferences, things like that, that's what we use IndiePie sponsorship for. We used to in real person, maybe we'll do it on May, go around the room and see who was hiring and who was looking for a new career. So you can do that virtually over on the IndiePie Slack channel. So there is a jobs channel in our IndiePie Slack org. If you need an invite and you're not on there already, you can just go to that bit.ly link and we will put it into the chat. I think Laura probably already put it in the chat. I can't see the chat from wherever I'm at, but check that out. Post in there if you're hiring and post in there if you are looking for a new career opportunity. We would love to help get people connected so that they can make awesome work together. We have moved to meetingplace.io. So if you've not taken your meetup.com profile over there, please do. Go to this address, meetingplace.io/indiepie/claim, answer a couple quick questions, and your profile will automatically be migrated over to meetingplace.io. If you want to be in the running for the door prize tonight, you do need to be RSVP'd on meetingplace.io by the time I finish the talk tonight, because I will do a live Python code and we will grab the RSVPs as we speak during the demo. So make sure you're RSVP'd there to be in the running for those 3 awesome door prizes. Oh, look at that guy. That's me. So this guy over here is going to be talking to you tonight about predicting lightning strikes. So let's do that. Unless there's any questions, I don't think there should be. We'll close that guy out. There we go. Now the reason you're all here. It does sound pretty incredible, but we did work on a recent project. And also during this presentation, this can be pretty interactive. So feel free to chime in with questions. Actually, let me get the chat up here so I can see the chat. If you have questions, don't be bashful, throw them into the chat. I will try and answer them. Or even better, turn on your camera, unmute, and just holler out at me. I'm happy to answer any questions. We're going to talk a little more about a couple bits of the technology that I think were interesting on this project, but I'll give a quick intro to what this project was about. Normally, I'm presenting this with the lead tech developer from the Flash Scientific Technology group, but Will couldn't make it tonight, and that's okay. I can stand in for Will. Although I don't have his cool hair, he's got the cool like Colorado skier dude like hair. I don't have that. It's okay. I'll do my best to make my Will impersonation credible and believable. So this project was something we've done over the last 12 months with a group called Flash Technology. So you can check them out online at flash.technology. But I want to just give you some of the kind of cool backstory on some of the technology that helped make this possible. But I will kick it off first with what the group is and what they're doing and why this is actually even important and why you should even be paying attention. If you didn't catch it from my earlier intro, my name is Calvin Hendryx-Parker. I am CTO and co-founder of 6 Feet Up. We are a Python and cloud consulting company, and we help bring these crazy ideas to life. We do some really fun projects, and Flash was one of these cool projects. Now, if we look at the Flash project, let me bring up my notes real quick. What's really interesting about predicting lightning is you would think this is like a solved problem. When you get a lightning or thunderstorm warning on your phone or you listen to it on the radio, those are based on where lightning is right now and not where lightning will be. So those warnings you get are based only on what we know about. There's lots of sensors set up that can detect lightning in the atmosphere, and then they can triangulate where that lightning strike was and what time it happened. But up until very recently, there was no way to know 10 minutes or even 25 minutes ahead of time where lightning was going to be. And this affects a lot of different industries, especially industries like the airlines, for example. I got a couple little notes over here. Delta Airlines, for example, is one of the case studies that Flash is working with right now. They lost $125 million in revenue due to a continued 30-minute ground stop rule from storm activity on one day in April a couple of years back, like 2017. It canceled flights and it continued for 5 days of disruption. So you can see that if we could narrow that 30-minute window, they can basically save up to $30 million by being able to narrow that window down, by being able to know exactly where the lightning is going to be, as opposed to the kind of more broad, conservative stance that these organizations have to take when you're dealing with lightning strikes. I mean, no one wants to risk, obviously, a plane full of people crashing. So you have to be really conservative about when you actually allow those planes to then take off and land on those fields. So being able to know more specifically where the lightning is going to land gives them a big advantage as far as like saving money on revenue and things like that. This other example I have up on the screen right here is actually a real life example from Tampa. For those of you who don't know, that Central Florida, like Tampa region is actually it's the most densely populated with lightning incidence areas of the United States. So more lightning happens there than anywhere else in the whole of the United States. But there's also a lot of people doing recreational activities in Tampa Bay. And this is an example of a lightning strike. And you can see on the image on the left, no, sorry, the right, the image on the right, the algorithm was detecting lightning. You can see the red dots off to the left of the bay right there. The pinpoint on the map is actually a jet skier on the bay that day. So these are potential lightning. You can see them right here. I believe that it was 25 minutes before the actual strike happened. And then you could see they predicted at 3:13, so that was 3:10. At 3:13, you saw the lightning move from just east of the jet skier to straight over the jet skier at 3:13. The jet skier was hit by lightning at 3:37. So if they could have at 3:13 known that 25-minute window was closing in, they could have actually called out to all the people who had rented jet skis on the bay and gotten them back in and saved a life. The initial 911 call came in then at 9:40. So this is actually replayed against lots of different data. So the algorithms itself that do the lightning detection take into fact the radar scans and a lot of the atmospheric data to produce a model that can give you this 25-minute ahead of time probability, like to a 95% probability of where lightning will strike. And so obviously saving lives is great. Being able to alert parents who are at maybe at a ballpark or a baseball game or out at the playground, being able to give them that heads up to be off the playground. Lightning strikes are seriously fatal and very real possibility for a lot of these folks out there. So really, it's an important technology that is kind of now coming to light. The original algorithm was developed by Jason Dietz, who is the meteorologist for the National Weather Service in the Atlanta area. And that's actually who contacted 6 Feet Up to help take his idea, which was a IPython notebook at that point in time, Jupyter Notebook at that point in time, and productionize it into something we could run in the cloud. And so that's the part I'll talk most about, is the running of this algorithm in the cloud. And basically we were tasked with implementing that cloud native solution that capable of low latency requests and responses. The initial notebook would take, I don't know, up to 30 seconds to 90 seconds to process the radar data, the atmospheric data, and produce a graph or a plot showing you where those points might be. But we needed to get that down into sub 1 second levels to be useful for production, because you want to be able to scale this out to whatever business partners are looking for lightning prediction data. And so that was the task at hand. That's where we are at with this project. The project challenges is there's a lot of data, and there's a lot of interesting data that's actually open on the internet for you to grab. For example, the National Weather Service, the NOAA NextRad data, is actually stored, or they have hosted versions of that data in Amazon S3 buckets, and they actually update in real time as they add new scans into those buckets. So for example, a full radar sweep scan comes in, basically you get an SNS notification on a queue saying that there are new scans available for you to read. And then they have like archive scans, and archive really means kind of last, I think it's 6 minutes to 10 minutes. Or you have real time, which is however long it takes. I can't remember what the timing is on the sweeps, but like 60 to 90 second timeframes for new data coming into these S3 buckets. And those scans range, you can see here, from 3 to 15 megabytes. So you can imagine, as you look at the 159 NextRad stations and 49 TDWR stations, the amount of data can start piling up really, really quickly. And you want to make sure you're only getting data or processing data in a way that allows us to scale that horizontally to consume that much data all of a sudden, or not all of a sudden, but like en masse. Another part of this ingest is called RAP data, rapid atmospheric. I can't remember what the P stands for. I'm not the meteorologist. I'm merely the cloud guy. Kind of a good joke. I just pulled that one out of my hat. But the RAP data itself is also 450 gigabytes of data that's ingested per day in addition to these Next-RAD scans. So there's just a lot of data that comes together to build these models. And what's also happening on the Flash side of things is they're also including new data sources all the time. So they're adding in HMRS data, HRR data, GEOS data, and they're doing other things for other machine learning projects so they can start doing more predictions, not just lightning, but things like tornadoes or other weather events. Those are all on the horizon for the Flash group itself. But the forecast delivery, we want to make sure we got the forecast delivery underneath 500 milliseconds so that it would be more usable for production usage. So the original, here it is. The original Jupyter Notebooks took 30 seconds to produce a forecast. Our goal was to get it down to under half a second, so 500 milliseconds, and do it using portable standards. Like most of the data exchange right now is still using JSON or GeoJSON, so that it was easy to deal with those data formats before having to scale into something that's like more binary. One of the things we did though with this project was go cloud native from the start. You leverage as much serverless. We don't want to be managing servers and upgrading and patching Ubuntu and Linux and things like that. It was actually really important that the project could run lean from a operational standpoint of like the humans needed to operate all the compute resources, and being able to stay cloud native actually reduced that overhead for us. So we've got the portability of the data all kind of aligning around the compute. So specifically, we used Lambdas, Elasticache, and those were working together on the front end to consume most of the data. And on the back end, I'll show the release process, but it's a lot of Lambdas and running all the things running in containers, which actually made it easier for them to deploy and start to consume other data sources very, very quickly. I also wanted to focus on making sure that the local development experience was easy to spin up new developers onto the project, because as they start to scale up, they're going to want to be able to bring on more developers, have them be productive from day one very easily. So let's talk about the develop. We're going to start with the developer experience part of the journey. And so being able to run locally on your system is very important to be able to iterate quickly across your project. If you're constantly coding either in the cloud or waiting for a CI environment to run before you can actually see your changes take effect, you're looking at long iteration cycles to actually get anything done. But if we can actually have the developer experience, you can see right over here that we're using Docker Compose locally to run the various containers, or using things like the Lambda images can actually run locally. And so you can test things like your SNS notifications by simulating posting those events into your Lambdas, running those as test cases, doing unit testing against them, all that before it even hits the CI environment. Down at the bottom there, you can see we've got the AWS console, the CLI, all of that kind of click salad initially to set up Lambdas and try things out. We eventually turn that into Terraform that will be run by the CI environments, so that we can spin up new environments or new Lambdas for new data sources quick and easily, and in kind of a nice controlled fashion. So bringing on a new data source, the client, Will, actually told me that he had planned a 2-week sprint to bring on a new data source. But because of the way the project was laid out and kind of the way the code had been split up and the way we focused on using Lambdas and serverless for the ingest of new data, he was actually able to bring on a new data source in less than 2 days. So from 2 weeks to 2 days was a huge acceleration in their sprint to bring on these new data sources. So in addition to the local developer experience, this project specifically is using GitLab for the source code repositories and for the CI and CD environments. And then we'll have like hooks into things like Slack for kind of not full chat ops, but at least notifications that like builds were done, code was committed, tests ran, things were successful or failed, was also very important. All of the infrastructure beyond the developer's laptop is all controlled with Terraform. So every piece of infrastructure you see on the screen right here, the Elastic Container Registries, the Lambda instances, the S3 buckets, the Fargate tasks, and the, oh my gosh, what's that thing there? I'll get to that one in a minute. Oh, the artifact repository, all that's controlled by Terraform. So any new infrastructure needed, it's Terraform first. It's not going to the console and clicking through and making basically irreproducible infrastructure designs. That stuff is now reproducible, so that if you wanted to redeploy this to another region or redeploy the same pattern for another project, you can pick up that Terraform and plan and apply it against another region, and you should be good to go. The initial proof of concept we did was a little more monolithic, and then as we started to build and build on top of it, we were able to pull out some pieces. That's what so if you look right here, so I'm looking the wrong way because I'm like mirrored from that thing, but over here on the this is the artifact repository. We started building some common libraries that all of the Lambdas and the Fargate instances will all leverage, so that you can actually test those pieces independent of the Lambda or the Fargate task through the CI pipelines themselves. So being able to refactor or kind of factor out those commonalities allows us to now process the model at multiple levels across this infrastructure. And we loved using containers. If you've used AWS Lambda, you'll know that you can use multiple different languages, Node, Java, Python. I think they support Ruby. They've got basically, if you were to go through the AWS console and click through there. So if you're using Lambdas, you can actually pick any of those runtimes and basically paste your code into a text box on their web page inside the console to basically make your Lambda handler. Another option is to upload a zip file into an S3 bucket and point your Lambda at that. The third new option, which was announced like a year and a half ago at the 2020 reInvent, was the support of containers for Lambda, which is pretty awesome because basically our whole pipeline now runs very similarly. Whether we're using Fargate or Lambda, everything comes down to some Docker files with containers that are what we actually deploy out into the cloud. Now, that is tricky if you need things like C dependencies, for example. Let me come back over here. If you are using a C dependency, normally this is kind of how you would do a Docker image for Lambda. You would use one of the base AWS images for Lambda, and you would, here in this case, I'm copying the requirements file in. I am doing a pip install of the requirements file, copying my, my app, my whatever I'm running in that Lambda into my container, and I set up what the command is going to be for the entry point when that Lambda runs. Very simple, very straightforward. This works great if you have a pure Python project with no external C dependencies. But in this case, we're doing a lot of scientific data science work with Lambda, and we're going to need things like NumPy, and there's another wrap library, some more data sciencey type things that were specific to using C libraries. And there's a way to do it, but it's not obvious necessarily. You basically need to do a multi-stage build inside of your Docker file. So if you're not familiar with the multi-stage build, you'll see that extra keyword at the end of the from line on the top there as build. That comes into play later after we do all the builds. So we'll basically have a Docker file at the top that looks like a standard Docker file. In this case, we're installing onto the Amazon Linux 2 base image, which is what the Lambda images are based off of, which is why we can use this. They're going to be compatible. And you'll see later, we're going to use a different image to copy our stuff that's been compiled in our build into our Python-based image. So in this case, we're using Python 3.8. We install all of our Python 3.8 dependencies that we need, and then we install our dependencies. So you can just run the standard requirements file. You'll notice here the no deps and no cacher. These are some optimizations to make the Docker images build a little faster. And also, we pre-compile our dependency list into this requirements.txt file from an .in file, which has our shorter list of the main direct dependencies in our code. Any leaf dependencies, we actually compile in using pip tools. I'm a big fan of pip tools. I find it to be a really reliable and quick way to manage dependencies. You get hashes, you get all the version pinning, and this helps us achieve repeatable builds in a Lambda environment using Docker containers. So the second half of this, so this is the first half, you'll see that we're actually building those and putting them into /app/wheels right there. That comes into play here where this is all one Docker file that's been split in two, so I can show you on the screen. This is the second half where we're actually using that same Lambda base image, the Python 3.8 base image. We set up, bring in our requirements file. We have, you can see right here, this is the key bit. We copy from our build that happened above, our app/wheels, into this image's app/wheels. Once we have those pre-built wheels there, they're ready to be installed. All the platform-specific C stuff is all bundled into those wheel files so that it can actually run on an image that doesn't have the C compiler on it. So we install from app wheels with a requirements.in. So that's the one that has just the direct dependencies on it. The pip will do all the dependency resolution. Basically, it says, just install all the stuff that I pre-compiled for you in that wheels folder and go. And then same as before, copy the app.py into my image and set up my entry point. And now this is ready to run on AWS Lambda. You just point some Terraform for that Lambda, specify where the image is. So we upload that image into the Elastic Container Registry. And that's how we deploy these images with Lambda. Just checking to see if there's any questions.
Calvin, at what stage does that run? Is it like a one-off thing you do at the beginning to create your images, or does it run at the beginning of each Lambda execution?
So the beginning of each Lambda execution will basically grab, as it spins up, it grabs the container from the container registry and spins it up inside the Amazon infrastructure. So Amazon will keep, as it scales out, because basically Lambdas are designed to scale horizontally. And so it will copy that image into multiple, virtual machines that are running all these images, and it'll keep them warm for some time. If you have a lot of traffic and a lot of hits coming in, it won't just throw away that container, turn it down. It will actually try and service multiple requests from that same container. So the performance can actually be pretty reasonable. And there are some tricks you can do if you have a specific use case that needs more long-running compute like that. You can actually do a keep alive to keep some of those images around so that you aren't going from like zero absolutely cold. But the images are all pre-compiled, in the CI pipeline, uploaded into the container registry, and then from container registry is where Amazon grabs them when it needs to invoke, more Lambdas to service your requests. And the images themselves are completely immutable, so you don't write any data in the image. You can. There's a new announcement. Oh boy, last week and a half ago, about Lambdas getting more storage space, more ephemeral storage associated to them. If you have a use case that needs it, that's awesome. But Lambdas are really meant to be short execution time. You can go up to I can't remember what the new maximums are, but they had a 15-minute execution time with some maximum number of RAM. But if you do that, you are going to break the bank. Those get very expensive to run, as opposed to if you just had spun up like Lambda tasks, or not Lambda tasks, but Fargate tasks as the same container over in a Fargate cluster that were just long running. So you kind of have to balance that out to get kind of a cost, find out what your most optimal kind of cost path is, depending on the characteristics of that workload. Any more questions before I move ahead? But this is a really good example. There is a blog post on the 6 website that I linked to, I think, at the end, and we'll include it in the recap that I show off all this step by step, how to build a kind of a best practice multi-stage Lambda container that includes C dependencies. Okay. So once that all is like deployed, the deployed experience, this is like what's running in production, is going to be Nextrad data. That's what the NOAA logo is over there. As Nextrad data is dropped into the S3 buckets, the SNS messages are picked up and processed by the Lambda. So the Lambda over here is the first one that's going to pick up Nextrad data, run it through the processing, and then the results of that processing, we cache over in Elasticache. So that Elasticache over there is handling all of the quick access to the pre-process, kind of post-processed data. And then there's also some other processes in there that basically archive the data off. One of the features of this platform is we can actually rerun our predictions against archived data against real data like lightning strikes. So I remember I mentioned at the very beginning, current lightning strikes are based on sensors that detect real-time lightning and where they're at. We actually have a feed of that lightning data coming into the system that we can actually run test cases against to validate that our predictions are in line, or maybe they're drifting one way or another. So that's how that works. So these are the Lambda instances that ingest the data. The APIs themselves are deployed as tasks on Fargate. So those are Django REST framework on the back end. And they also talk to the same Redis cache to basically grab that post-processed data and serve that out as part of the API calls. So that's how we've managed to get the forecast times down to under a half a second, is that most of the things are pre-calculated at a periodic rate as the data is available. We pre-calculate a lot of those forecasts for known, like, I guess we would register specific radar stations that we would be interested in to have those pre-calculations for. So we pre-cache a lot of that and stuff it into Redis. Speaking of Redis, Django Redis and Redis can be tricky to deal with if you're not careful. If you're just using Django and you're just using Redis for a cache inside of Django, all will be well. It's a great way to speed up an application. But if you want to use that same Redis cache that you're using in Django outside of Django, that's where the trickiness comes in, is that the Redis cache for Django is doing some specific formatting, some specific serialization, but it does include alternate cache classes and alternate serializers, so you can actually use Redis from an external source. So keep in mind, we probably burnt a week banging our heads against why we weren't able to get the cached data to serve out of Django when it was coming in from an external source. So what is nice, though, is that the Django Redis package itself supports alternate serializers. So it is possible, it's just not obvious when you go to do that. I mean, Redis is an amazing tool for speeding up the delivery of any application, and I highly recommend it. On the front end of this application, we also still leverage things like CloudFront and the web application firewall. Any static resources are obviously served directly out of S3 buckets, and any other serverless bits we can use. So in all this infrastructure over here, there is nothing that is a running virtual machine, classic style, log in with a shell type system, which is nice because anything you can log into with a shell, greater chance for vulnerabilities and for attack surface area. The only exception is, for example, we may have a Bastion host that's running an EC2 instance down here, so that we can actually access things like the Postgres instance, from behind the firewall. So nothing is exposed in a public subnet. Everything's actually, done in private subnets, so that we don't accidentally expose, a database instance to the internet that's not supposed to be. I don't know why anyone exposes any database instance to the internet, but we make sure we don't do that based on the infrastructure that's all set up here with Terraform. And so kind of next steps from this project, we did a postmortem. One of the things that was probably most tricky to deal with was when you're doing cloud native development and you need to get event-driven Lambdas to run in response to like an SNS change, for example, is that we didn't have that locally. So a lot of times we were faking it out by passing the data in as like JSON blobs from the command line to play with it. But sometimes you want to be able to see it run start to finish with semi-real data. And so we were actually able to you could do that with a tool like localstack.cloud. If you've not checked out LocalStack, this is something we're going to start adding into a lot of our cloud projects. Is it allows us to run a lot of more of those cloud native bits from AWS locally on the developer's workstation using Docker Compose. So with Docker Compose, you would spin up and say, I want to simulate S3 buckets, SNS. I want to simulate these Lambdas. I want to simulate, it supports a whole bunch of the various cloud services. The one bit would be you'd have to probably write your own shim piece between the SNS notifications coming from the actual Nextrad buckets if you really wanted to simulate those being replayed in your local environment. So that's something we haven't done yet, but it's definitely on the table for next steps. There's a definitely speed up because right now, when we got into needing to test with the real data, there was a whole wait time from commit the code, wait for the CI pipeline to run, wait for it to deploy the Lambda images, and then we could see it run. So kind of like that, the XKCD of what are you guys doing out there, playing around and waiting for it to build. We're waiting for it to run CI basically at this point. But tools like this exist that can actually help speed that up. Another thing that was tricky is basically if you're dealing with Code Artifact, which is their version. If you're familiar with JFrog's Artifactory or like PyPy, Code Artifact is basically a hosted in the cloud version of PyPy, where you can put your wheels into that repository and then install them from your private repository, and you're never publishing your code or your wheels to the public at large. If you're using a tool like that in your build process, it can get tricky if you're doing the build process in an external place like GitLab, where you may have to have secret access keys and tokens to be able to access the code repository over in Amazon, or the wheel repository over in Amazon and Code Artifact. I think one of the things that we would probably fix up for next time would be to run more of the CI pipeline that's dealing with those private packages in Amazon's code pipeline. So using code pipeline and code build in AWS, you can give those infrastructure pieces IAM roles that grant them access to the bits they need when they need them, as opposed to dealing with secrets and keys and possibly exposing those kinds of things, running them in a different CI pipeline. This is a great argument for staying inside that platform and using the IAM roles to be able to protect those resources. Some things that are coming up from the scientific side of this next project is going to be how to go to a full streaming model. The initial implementation of this was doing the archives, which are the 5-minute snippets, whole snippets of the radar scans. And we want to be able to move to those real-time scans as they come in. So that's the next kind of pseudo streaming implementation for the Nextrad bits. But since we're already on Lambda and we're already getting SNS notifications, it's more of a matter of refining the algorithms to be able to handle that level of data streaming in. For the first implementation, having 5-minute old data is satisfactory for the predictions. From here on out, the predictions are only going to get more accurate. And they're going to have more data sources brought in to start computing even finer grained predictions against different parts of the model. So those additional data sources, the MRMS, the HRRR, they're going to give more granularity to the model as it goes to predict those bits there. If you have more questions about the science behind all this, you probably want to talk to the customer, not me. I'm definitely not the data scientist. I just made a thing run fast in the cloud, which is what I like to do. And this is kind of the mock-up of what they're talking about. That Nextrad real-time data, they're talking about adding in some additional inference instances. This is the case where I think they initially mocked it up using Lambdas to do some of the inference, but because the Lambda runtime was taking more than a few seconds, the bill started going up and up and up and up and up. And at some point, it makes more sense to really either spin up Fargate instances or an EC2 instance that has the appropriate GPU that would make sense for whatever models you're specifically running. So a lot more is coming from this group as it comes to doing inference and GPUs and doing a lot more machine learning against it. A lot of the initial algorithms are a lot of regression type data statistical analysis as opposed to true machine learning models. And that's it. Thank you all. And if everybody's got questions, I'm happy to answer them specifically from the cloud perspective of things. I can try and answer some weather questions, but that's not my forte necessarily. So feel free to turn on your camera and unmute and ask away.
Hi, Calvin. So one part runs on Lambdas and the other part runs on Fargate, right?
Correct.
Okay. What would be the biggest advantage of not having everything on containers on Fargate?
Because some of the things do run so, like some things run like once an hour. And if you're running once an hour, I don't think you really need to spin up a Fargate instance to run full-time 24/7 because Fargate instances don't scale to 0, where the Lambda instances do scale to 0. So that's the differentiation there. Let me put that back on.
Yes, you're right.
It's based on the workload. So if the workload is spiky and only happens periodically at some specific interval, Lambdas make a lot of sense because it's very, very cheap to run them depending on what the workload is. As soon as that workload starts to extend in time, compute time, the Lambdas can get more expensive. But you kind of make up for them scaling to 0 makes up for how expensive the compute is in the short burstiness that they are used. So really it comes down to cost.
Okay.
Under the covers, under the covers, they're really running on the same Nitro hardware, and like the firecracker system.
That was my second question. How hard is to change one process from Lambda to Fargate and vice versa?
It's probably fairly trivial. You may have to add in more, if it's exposed publicly, you'll have to add in some more authentication or authorization bits probably to your code, as opposed to like if you're using API gateway, you can specify those things as part of like API gateway. You'd have to do that in your code on the Lambda, or not in Lambda, the Fargate, if you did it on Fargate. But otherwise, it can run any container, any task you throw at Fargate as a container. You just launch it as a task, it will start handling requests. But they'll be long running. And so Fargate will auto scale. So kind of, if you picture like EC2 instances and then Lambdas on one side, Fargate's kind of in this middle spot where it's long running, but I'm not managing a VM and the operating system. And also I can do auto scaling. So like with the EC2 instances, you can auto scale. With Lambda or with Fargate, you can also auto scale. You could specify a criteria by which the number of tasks servicing those requests will scale up, and they'll automatically be added into the load balancer, the application load balancer. So this is a similar architecture to what we do with LoudSwarm. So if you came to Python Web Conference last month, we host that on Lambda or Fargate. Oh, good Lord. Fargate. We host that on Fargate, and we actually scale up, as there's more users viewing the content, we can scale up the number of containers that are handling things like the WebSockets or the API calls to match the users. But the downside is it doesn't scale 0. I think that's coming. That's a feature request we've been making to AWS, is to have Fargates that could scale to 0.
I think everyone is asking for that.
Yeah, for sure. Well, it's kind of the best of all worlds. Like it's much more flexible containers, much more flexible like instance sizes. You can run as long as you want, or you can have it scale to 0 for like ad hoc tasks. So it'd be so nice. Cool. Any other questions?
Calvin, how do you, let's say you get some really bizarre prediction out of it and you want to go back, and yesterday was a sunny day and you got some prediction of lightning in Indianapolis.
Yeah.
And you want to go back and replay things to see what was happening, or essentially debug. Like, what's the process there?
So all of the API calls we built into the system allow you to specify a start date time as an optional argument. So basically you can kind of go back in history to replay if you, for example, maybe you wanted to like see what the results were giving you yesterday. Maybe you wanted to run the library, like update the library, make a change to the model and rerun that API call again. You can. So the call could be called multiple times against different versions of the library if you wanted. Now, right now, we don't have the ability to release multiple versions of the model simultaneously, but you could maybe have a V1 model, a V2 model, a V whatever, revision of that model to compare the same results against the same data, or to get whatever the results were, the different library versions against the same data. That's possible.
That would be running in the cloud, right?
Yeah. Oh, yeah.
So you'd have to, let's say you wanted to play with some new model feature, you'd have to release that model and then call it through the API. Okay.
Correct. Yeah. I mean, you could do some of this locally since if you've got the right IAM roles locally. So if you've assumed roles locally and running your code, you could access the S3 buckets where the archive data is, or you could have a VPN connection into the database server or to the Redis cache, because most of those things are all read-only. Like the data is being written from the Lambdas into those places. The predictions are also being written into the database for comparison at a later time. But I think it's a fairly safe operation to read those from a local developer workstation if you were wanting to iterate quickly.
And how much data is stored?
I don't know what they've currently got. We don't store all the wrap data because, again, that's like 450 gigabytes per day. I think what's being stored right now is historical Nextgrad data that was used in any of the predictions. We store that, and then we store the prediction so we can compare them again if we wanted to know what happened. And then we're currently storing the actual lightning strikes. So we can historically look at real lightning strikes compared to the model's performance. I mean, it's pretty cool when you're working on it. And like, we're here in Indiana. I can literally put in my, lat long coordinates of where my house is. And if I saw lightning or I hear thunder in the distance, I can start seeing the points plotted as lightning's coming across the golf course here. It's pretty fun.
I wonder if you can use it to bet on sporting events then, if you have some delay of game wager, something like that.
So speaking of sporting events, the group, like Will and Jason, were actually part of a pit crew at the Daytona 500 this year. So one of the pit crews had them come in, they got to have their logo on the car or whatever, but they were doing live predictions throughout the race to let them know what's up. I mean, just think about the kind of competitive edge for predicting lightning can bring you. I don't know, kind of mind-bendy where that could go.